Okay, guys. Andy, Bianca, are you ready to go?
We are.
Okay, excellent. So I got the sign that we can start. Hello, ladies and gentlemen. Welcome to our live session regarding distributed manufacturing in the context of additive. I'm Marius, and I can tell you, I'm excited. It's my first time doing a virtual question and answer session, a live one. Typically, in nowadays, we would be at Formnext in Frankfurt. So now it's a digital format, but I think it's a nice opportunity also. So each of you guys, you can just sit down where you're comfortable. You can ask questions. We don't have to travel. We can make up our mind about other technological questions maybe. So hope that some of you guys joined our sessions regarding distributed manufacturing. So yesterday we had a talk on the basis. What is distributed manufacturing? So I think there's not the one answer to how to approach it. But I think with the circumstances that we have now, due to the kind of things that's going around or other political topics and so on, I think it's a great opportunity for the whole industry, not only additive. But it's only my personal opinion. So I think no one waited on distributed manufacturing that it will start or it will be a chance. No, I think it's the combination of different pieces of technology, bringing them together, and then you have got an extraordinary nice solution where your company, your organization can benefit from. So bringing additive together with automatization, software, digital environment can be a real mighty tool for your company. So do not wonder, I just look sometimes in my tablet if there's any kind of question going on. And I think I have the first one. Are you working with specific automatization partners together, or can you simulate and integrate all kinds of automatization manufacturer? So I think this is the perfect question just to start our discussions. So typically we focus on our core business, what we are doing. And this is actually AM. So that's why we really try our best to make our machines, our equipment as open as possible. That means that these machines can be open to your specific demands. We have our heart, our process, our machine, our material, and then you can plug in industrial ways of producing. So for example, automatization, post-processing and so on. So we defined different kind of interfaces that are open to nearly all different kind of equipment and also software, not only hardware, to join, to connect your machinery and then start your production. So just to sum it up, I think yes, definitely we are open to all kind of different manufacturers. Of course, we have got also preferred partners where we also did the first digital production environments, like for example with Siemens, with KUKA, with Grenzebach or other robotic providers. But there we have already a proven solution. But as I mentioned, we are open to all kind of other possibilities. So I just have a look. Another question: how detailed needs to be job or facility information to start a first simulation? I think this is a good and a complex question. So let me just make up my mind. The whole process starts with having the right application. That means as soon as you have defined your best fit for AM, like this one, my colleague Alois, we need basic information about the duration of a build job, for example, with different parts on it, or one specific build job dedicated to one application. So at least the duration of the build job, we need the quantities, and very important is, due to powder consumption and material consumption, would be ideally the volume of each application. As soon as we have this, and of course the material, we need to know which material we want to produce. Is it a specific polymer in metals? Which kind of metal is it? Is it aluminium, titanium, Inconel, and all these kind of wonderful processes that's going around? And then we can start our simulations, because then obviously we see which machinery is suitable. In metals, for example, would it be an M4 system, the very big platform? Is it the M2 system? Maybe even the very small ones. So we can do also connected machinery and digital production by the M1 systems, connecting them with software together and bring them in a digital environment. So even there are nice possibilities for simulation, but also then for real production. So these would be the basic information: job duration, dimension XYZ, quantity of parts, and the materials. These are the basic information regarding the application. Afterwards, starting the simulation. So when speaking about digital production, a digital production twin, we can call it, then I would need your preferences. That means, is quality the most important issue? Obviously, speaking about aerospace industry or automotive or medical, of course, then for sure this would be. Or are you extremely cost sensitive, for example, because you want to produce high quantities for a specific industry? Maybe this is your biggest trigger. Or time. This could be also a very interesting one. So I think these would be the main questions. And then we can have a look if there's an opportunity for connecting your production. Do you need a high grade of automatization in terms of bringing build jobs from one state to another station? So shift models. How many people should work in your environment? These are questions that we ideally would discuss in the beginning. So hopefully this was a kind of answering your question, guys. I have a look if there's something new upcoming. Oh yes. How much time on average does it take from part screening to serial production? Oof. This is, I think the questions go more and more into a specific way that hopefully I'm not struggling answering it, because how much does it take? So, this is a very good one, because I can just tell you, we've got now, and I'm very proud about what we did at EOS with our department, with our digital department, how we could bring a specific B2C application now into serial production within 6 months. It was about 6 months, a polymer production that we could, from first design iterations, from iterations regards all post-processing, regards quality, regards warehousing, and all these kind of processes around, within, I do not want to say something wrong, but it was not longer than 6 months. Of course, speaking about parts from aerospace business, when you have to certify everything up front, where you have to look on each process in terms of non-destructive testing, in terms of all quality assurance, and so on, and documentation. These can take years. But out of my aerospace background, I know that even these processes, we could reduce them dramatically. So I would say even by the half of the time. So speaking about one very interesting customer case with Airbus together for the A350 program. I think it took us not longer than 1.5 years from first iterations until certification of the part, and then another half year for the ramp up. So in total 2 years from the first design iterations to serial production. I think this is amazing. And guys, this fits more and more into the development cycles of the products of each industry. Looking at automotive, to my personal opinion, to my mind, this will be one of the most important industries for additive in the upcoming future. New possibilities in terms of electric drive or other engines that might come up for serial production. More and more modifications in the different cars. So I think this will be also a great opportunity for us, and then matching the development cycles of each car can be the perfect fit for additive, being quick. We don't need to have all these kind of toolings, preparations and stuff like this. So I think there we can also get a really a nice fit. So hope this was also kind of answering a little bit the question. So it might be a very short cycle, even half a year, or even shorter when we really know which application, how to produce it, and then start our simulations. So I just grab maybe a cold water. Then let's see if there's another question upcoming. How detailed needs to be the job detail for the first simulation? I think this is something that I want to answer you very directly. We don't need that many information in the beginning. With our digital environment, we are very capable for informations. That means we love to collect data. So not that we store it and do it and have it on our own, no, to share it with you. That means we store the data that we produce then, analyze it, and try to improve all the time. But for the beginning, as I mentioned directly in the first answer, for the first simulation, starting the simulation, there's not more than a handful data points that I need. That means a rough simulation of the job length. And even this I do not need because I can do it on my own with all my systems that I have available. Basically, it's just the material that you want to go for in metals and in polymers, which process I can choose. This is my core information. And then I would just need the XYZ dimensions of the application that you want to produce. I need the quantities and I need the volume of each part. This is it. With these 4 informations, I can directly start my simulations. Because as soon as I have built up the model, the environment, we can even call it digital twin. As soon as I have this, we can change and trigger and challenge all these kind of small little details that you want to get out of the simulation. This is the second step. And then we've got plenty of opportunities, hundreds of different ways to approach your production. And we figure out the best way together for your production and the way you want to produce your parts. But for the beginning, and this is, I think, the beauty of this approach, for the beginning, you do not have to fix that much on a specific way. I think even when you are not sure if something is the right opportunity or if it really makes sense, we can also help you to find it out. That means with this very few informations, you do not even have to find the redesign for AM in the beginning. This is not necessary for me. I just need a rough volume of the part, XYZ dimensions, and the quantities. And obviously, the last questions about the material, I think this is in many cases, or in most cases even, the simplest one. Because in most cases, you definitely know which kind of material you want. Is it aluminium or titanium? Is it PA11 or 12? So I think just reach out to us, and for sure we will find a simple way to approach a very complex way of thinking simulations, but the beginning is really simple. So now I have a look if there's a new one. Hi, can I include an external operation in the middle of an internal workflow? Internal, external. So let me answer it on this way. Similar like with the simulations, in terms of automatization, we have open interfaces to nearly all production technologies out there. That means starting our simulation model, our digital production twin, you can plug in any kind of digital hardware that is on the market. That means we need to understand some basic data points. That means, what is your machinery capable? Just assume, for example, a CNC mill. How quick is the grinding operation? How much material your grinding machine, your CNC machine, your CNC mill can remove in a period of time, in a minute, in an hour, or on a specific time frame that you have. These are some basic informations that we need, but honestly, nowadays I think 95% even of all machinery out there is available on a digital way, on a digital base. So that means I would think that we can get these kind of specific processes that you are maybe mentioning and include them 100% in our internal simulations. That means the complexity of this approach is to start the model once, as we have defined the model with our hard technology. That means first we make up our mind which kind of process it would be ideally. What is your focus? Is it time? Is it quality? Is it costs? Or is it all three of them? Might be also a very good one, the combination of these three aspects. We define a AM cell. An AM cell is a configuration of additive machines that brings you certain benefits. Mainly it's OEE, that means how to save costs by running these machines, running this configuration. It gives you also kind of economies of scale. So just assume the powder handling system. When you would run a bundle of machines, like 2 or 3 M400 systems, bring them together, plug them into an IPML system, an automated powder handling system that we have, it brings you benefits. You only need one machine to combine 3 of them, and this is an AM cell. So this configuration is very useful, and then you can plug in all the other steps that you need. Okay, then maybe another one. Can you give a concrete example how AM and distributed manufacturing helped a company cope with challenges of the pandemic? So, let me take one bit of coffee. So, Which kind of example can I tell you? Maybe two of them. One is very obvious. So please apologize that I won't name any customer names and be too detailed regards the application, but I will tell you the opportunity. So speaking about the pandemic, of course, this is not the nicest topic that I can go for today with you guys, but it's very obvious. We are sitting here and not today together in Frankfurt, so that's why clear there is a kind of challenge that we have right now and a kind of crisis. But the opportunity here was, especially in the medical sector, to react very quick. What is distributed manufacturing? Nowadays, we were getting used to produce in hubs. That means somewhere in the world or in the specific countries or areas, we had a production, a manufacturing hub where centralized ideas or let's just focus on applications were sent into, they're getting produced, and then on a very classical way, they're getting shipped to the end customer. This is the very, very simple approach. Or how we are used to it in our globalized world right now, because we can use economies of scale and save costs and so on. With distributed manufacturing, or due to the crisis, the pandemic, we saw that some logistics, that even some productions or even whole factories or regions were affected by this pandemic. We had shutdowns. Sometimes we had really the problem to get specific parts or products. So the opportunity here was for the medical sector, and especially for one company that provided this kind of breathe apparatus. So they could get, with help of our machines, they could very, very quickly not only get specific parts, no, but they could dramatically, radically reduce complexity of these turbines where you need for the breathing apparatus. You can reduce number of parts, the complexity of logistics, produce it in a very, very simple design out of polymers, make it a distributed production. That means you can make it in your own production if you have one of our machines or even from other AM providers. But they can also get the design sent out to one of the service providers that are locally somewhere in the region, send also out the information regards certification that they need to take care about, how you have to regulate the process, how you have to regulate certain things. And with this, they could react really, really quick. So it was amazing for a medical company that needs typically even years for kind of certifications, test runs and so on. They could do it in weeks. So this was really, really amazing. Another example I want to highlight was here the topic spare parts on demand once again. So one of our partners from automotive industry, they have had the challenge also before this kind of pandemic crisis, that they needed their spare parts very randomly. That means sometimes you need a spare part 5 times a day, sometimes in 1 week only 5 times, sometimes in 5 months only 1, or even in a whole year, no one of a specific part number. But the challenge is that when a customer wants to have the spare part, then it has to be quick. You need warehouses with tons, 100,000 millions of different parts that are stored. That means capex is really, really high. You need a lot of working capital. You need to store it. And after 10 years, when the part is there in the warehouse, you have to scrap it. For example, in polymers, because the material quality is not assured anymore. So we started this years before this kind of pandemic, the kind of way of thinking and transferring hardware into digital parts, into digital components. And now we were ready. And I think this was one of the benefits of this automotive OEM, that they could immediately start producing their parts on demand. So then maybe I will just have a look if there's something else. Maybe I just give by the end of the session a short summary. So, distributed manufacturing. As I mentioned in the beginning, I think, and I do not want to blame anyone or be unpolite, I think distributed manufacturing was nothing that someone was waiting on. This was the challenge that this kind of pandemic or even some political situations out there gave us, to our organizations, to our companies. But as I mentioned in the beginning, I think when you have a challenge, there's also an opportunity, and a pretty good one. So that means combining different pieces of technology, like additive, like automatization, digital way of thinking, software, and so on. And then bringing these together to have a solution for distributed manufacturing. But I see right now an urgent question: which material do you see is the most important one, and what is EOS offering there? A good one. So the one most important material, I would say, it's like with our machines. There's not the one that is the most important or the most beautiful one, but there are many beautiful machines, many beautiful materials. So I would say, let me answer it in a very specific way. I think speaking about polymers, I think we don't have to look on very crazy or fancy materials. I think the very, not simple, but the common ones that are well used, well known, PA11 and PA12, I think still they are state of the art. Even when we use them since more than 20 years, I think they are still state of the art materials in terms of what they can, durability, feasibility, the whole process. So still these materials are at the top of technology, how to bring them into different industrial usage. On the metal side, I would say this is a little bit more complex, because this is highly dependent to your specific needs, I guess. But also there, speaking about materials like for aerospace, all these kind of Inconel materials like EN718 and cobalt chrome and the others. I think here you have the greatest benefit that you don't have to remove that much material after producing, as we have a very narrow shape design of our parts, and this brings you the benefit, like the buy to fly ratio, for example. Typically with milling drilling you have 10:1, so about 90% of your material, of your raw part, are flaws in the bin. And we can produce really narrow to the shape what you need in the end. So coming from aerospace industry, I love EN718. But also which kind of other materials are very interesting for us. To my mind, it's titanium, as in comparison to conventional producing, you can produce titanium on a very cost-efficient way. And I think this is the beauty of this material. Also, two other very beautiful materials, still aluminium, and I tell you something new. We are working on an aluminum alloy process where we radically reduce our costs due to a very, very productive process. We reduce our build time. So this will become more and more interesting. But also specific materials that you know from automotive industry. We are working on processes that are very similar to sintered materials. That means you don't have to take this very, very the safety gas atomized materials from different alloys that you know, but they are atomized underwater, like you know it from sintered materials. Take a specific fraction of these materials, and then they can be wonderfully used in very productive processes for our machines. So I think this will be a great candidate as the next opportunity. Oh, I have even some other specific questions from medical sector. So, how useful is SLS in medical sector, and can it produce medical grade stents? You know, if yes, which is the most suitable material within 0.54 diameter? I would say this is now a real hardcore question. A real hardcore question. So I can tell you once from my expertise right now, yes, we are producing stents, and yes, there are great opportunities. I can tell you also from our pre-development department something that I can share. We started a group within our organization that calls itself Solution Engineering. That means this is a multi-organizational group of different people from different organizations within EOS and also our partner network that comes together and makes up their mind on a certain solution. And I will be happy to take this question with me, because whom do we have there? We have people from CTO organization, from process development, from pre-development, material scientists, but also the people from my team, from industrialization of AM, from digital department, from all different kind of departments, bringing them together and developing a solution. And for this specific question for stents and this kind of 0.4 diameter, I could tell you the following answer. First of all, we are working on a new laser spot. That means we call it a pulsed laser. That means you can build up very, very tiny wall thicknesses. I'm from aerospace industry, but I have certain similar requirements like with these kind of stents applications. That means you need to have reproducible thin wall thicknesses. That means about 40 micron, something like this, is the wall density, the wall thickness. And it needs to be reproducible on a very, very long distance. So here we see the opportunity to take this pulsed laser, and I can tell you right now, I think my guys from CTO organization, they have to maybe close their ears when I tell it, but we are very, very close for industrializing this solution. That means we have tested it already. We have machine configurations in our pre-development department. We are doing this already. So we can achieve with this kind of combination of the laser, this kind of specific steering of the laser, we can build up this very thin wall thicknesses. And then another component would be my material scientists. That means together with these guys, we would have a look on a specific material that might be useful for your products, a specific titanium grade or stainless steel or another material that might be useful for your stents. And then have another friction of your powder sizes, not 5 to 50 microns, but for example 5 to 35 microns, for example, depending to the mesh of the sieve that you are sieving then your powder. And this might be then a good opportunity also to trigger the process and so on. And then there might be a great solution even approaching stents for serial production and usage for medical industry. So I would say this question, to approach this question, I would be very happy maybe even to speak a little bit more in detail regards this when you just contact me personally. Because I'm pretty sure if you would tell us your requirements, your specific needs, and we see an opportunity from technical and also our economic way for you within these kind of product range, then for sure there might be a solution. And with our solution engineering team, we could together develop something. So just feel free to contact me after the session on LinkedIn or via my professional email, so just approach me. So let's see if there's another question upcoming. Maybe I just wait for half a minute. If not, then I would say it was fun for me. Yes, I can tell you guys. It was unexpected because it was something new. I was never on this kind of semi-virtual and digital couch sitting here with my colleagues out there who assist me here during this kind of session. But I can tell you it was fun, and I would be very happy to make this once again. Or if you have any specific demand or on a specific talk regarding distributed manufacturing, production, or any kind of digital production content, or even other things, then we would be very, very happy to make this setup once again and reach out to you guys. So I can tell you, thank you so much for joining this session. I hope you also had at least a little bit of fun or got some new insights of what we are doing, in which direction we are heading out at EOS. And I would be very happy to see you soon in this digital environment. Or for sure, there's still my personal hope to see you once again also physically in person, Formnext 2021, or on any other additive event upcoming soon. So, wish you all the best, stay healthy, have fun with additive, and hopefully see you soon. So, bye bye.